All right. Were they giving away free Starbucks today? Lots. Everybody. The other classes. All right. So we're going to talk about polar coordinates. About the Higgs boson not being allowed in the Catholic Church. That was it. All right, so we're finally going to free ourselves from rectangles and from right angles and get into curves. We should feel liberated. So to start, we're just going to talk about what polar coordinates are. I know we've seen this before, so this should all be just a reminder. So when we're looking at polar coordinates, just what we're talking about is we have an angle in standard position. And our point here, we're going to refer to our point as P. Our coordinates are R and theta. And this is our angle. And we call this the polar axis. And this is going to be our origin. We call the origin the pole. And we have, I'm going to put R here. R is the directed distance from our origin to our point. And what I mean by directed is we can have a positive or a negative. So the direction matters. And theta we measure counterclockwise. It's a directed angle. And again, directed just means we can have positive and negative. And we measure counterclockwise from the polar axis to OP. So from the counterclockwise from the polar axis to the terminal side of our angle. So a couple of important things about polar coordinates. Our coordinate is not necessarily unique. Our theta is not unique. So xy, when we have a point in rectangular coordinates, that xy coordinate is unique. Our theta is not, because any coterminal angle with the same radius is going to be at the same point. So we don't have a unique point. And the way that we can write that just more in mathematical language, we can say r theta equals r comma theta plus 2n pi. So it can go around again in a complete circle, or we could have r theta equals negative r comma 2n plus 1 pi. So we can rotate 180 degrees and have a negative radius and be at the same place. So if I rotated around from here 180 degrees and said my radius was negative, that would bring me back to that point. So that's what the second one's saying. And the pole is the point 0 theta. for any theta. So if our radius is 0, no matter what our angle is, we're still at the pole. So just our basic terminology is how we're going to talk about polar coordinates. So one of the big things that we do in polar coordinates, we want to be able to convert. If we see something in polar coordinates, we want to be able to convert it back to rectangular coordinates. If we see something in rectangular coordinates, we might want to represent it in polar coordinates, because often polar coordinates are easier to work with depending on the situation. And as we move forward, we'll end up working in polar coordinates quite a bit, because often we're interested in things that have circular symmetry. All right, so let's look at how we convert coordinates. Again, we've seen this all before, so should be reviewed. So let me draw our axes, and we'll set up how we do our conversion. Nothing groundbreaking here. So here's our angle and our x and y. So this point is r theta, or xy in our rectangular coordinates. There's r. There's theta. I'm going to drop down a perpendicular here. So that's y. That side of the triangle is x. And just from what we know about trigonometry, we know that x equals what? R cosine theta. So y equals r sine theta. Tangent theta is y over x. And from the Pythagorean theorem, r squared equals x squared plus y squared. So these are all of our tools that we'll use to convert back and forth between rectangular and polar coordinates. So let's take a look at a couple of conversions. Let's practice with a couple of these. Just to remember all of this stuff, and we'll see a couple little things. That'll be good. 2 pi over 6. So we want to convert to rectangular. So x. What am I going to write for my expression for x? 2 cosine pi over 6, which is 2 times cosine of pi over 6 is square root 3 over 2. So x is just square root 3. So the other thing that comes up with polar coordinates often is unit circle stuff. So we get to remember all of that stuff. And y equals, that's everybody's saying hooray, right? Y equals 2 sine pi over 6, which is 2 times 1/2, which is 1. So my point, so xy is 2 pi over 6 is square root 3, 1. Well, it's nice and easy to go that way. Let's go the other way. So let's say xy equals -1 square root 3. So first off, where are we located here? We're in the second quadrant because x is negative. So we're looking for a second quadrant angle. So how are we going to find our angle? How are we going to find theta? Tangent theta is negative square root 3. So where in the second quadrant is tangent theta negative square root of 3? What is it? 2 pi over 3. So theta equals 2 pi over 3. Could we come up with another theta that would work? So if we're in the second quadrant, is our radius, and we're at this point, is our radius going to be positive or negative here? Positive. This is for r greater than 0. So could we come up with an angle for a negative radius for r less than 0? That would put us in the same place? So in the second quadrant, we're at 2 pi over 3. Negative 2 pi, would it be negative 2 pi over 3? So here, let's draw a unit circle. Here we are at 2 pi over 3. Is that right? 2 pi over 3 up there? No. Yeah. So if I go into the fourth quadrant, where would I be? Someone said it. Negative pi thirds. This is negative pi over 3. So theta could be negative pi over 3 in the fourth quadrant if my radius is negative, and that would put me back up at the same place. And then we find r, so we know that r equals the square root of x squared plus y squared, so r equals square root of, don't need that big a sign, 4. So r equals 2. So our points, we could come up with a couple of points in polar coordinates. We could have 2, 2 pi over 3, or negative 2, negative pi over 3. And any coterminal angle with these two would give us the same points. All right, questions on those two conversions? We're getting some gears turning again, thinking about polar coordinates and how much we love them. All right, so let's. The other thing that we want to that we will want to do with polar coordinates is we want to be able to convert equations to figure out what our graphs look like. So if we're looking at an equation in polar coordinates, we want to be able to convert it to rectangular coordinates, or back and go the other way if polar coordinates are more convenient to work with. So I want to think about a couple of how we convert some equations. And it's really nice with polar coordinates. We'll talk about cylindrical coordinates. We'll talk about spherical coordinates. When we start being able to think a little bit in a different coordinate system, we're so used to thinking in rectangular coordinates that when it's nice. It's an interesting thing that happens with your brain when you can think in a different coordinate system. So for these first few, we want to. I want to convert to rectangular. So we'll start off with some easy ones. First one, r equals a, where a is a constant. So what is that? A circle. Center is where? 0. So our rectangular coordinates start at the origin. So if we have a constant radius, where would our center be? 0, 0. And our radius is, this tells us, radius equals A. So in rectangular coordinates, this would just be x squared plus y squared equals A squared. So definitely in rectangular, or in polar coordinates, the equation of a circle is much easier. R equals A. That's a lot easier to work with than x squared plus y squared equals A squared. How about theta equals pi over 6? What would that be? If we graph this, what would it be? It would be a line. So for any radius, we're at theta equals pi over 6. And what would the slope of the line be? Tangent of pi over 6. The tangent theta is y over x, rise over run. So this is a line through the origin. And the slope equals, we know that, I won't say equals, we know that tan pi over 6 equals y over x. That gives us our slope. So the tangent of pi over 6 so let's go the long route. What is the sine of pi over 6? What is it? 1/2. And the cosine? 1/2 divided by the square root of 3 over 2, sine divided by cosine. So this gives me 1 over square root of 3, which is square root of 3 over 3. So there's our slope, square root of 3 over 3. So our line would be y equals square root of 3 over 3x. So, equation of a line in polar coordinates, a little easier to work with than equation of a line in rectangular coordinates. All right, let's look at one that's a little more complicated. R equals secant theta. Any clues here? What we would do with this? What is it? So again, Jacob? Multiply both sides by cosine theta, because our cosine theta is x. So x equals cosine theta times secant theta? 1. So in this case, rectangular coordinates definitely look a little nicer than. I love doing this. All right. Questions on those examples? Now plotting plotting polar graphs, plotting graphs in polar coordinates by hand, kind of tough. Usually you have to make a table of values. So you're calculating out your r and your theta for various values of theta. Thankfully we have technology that helps us graph these things. So pretty much anytime you will need a graph of a polar equation, and you need to find points of intersection, whatever, you'll either be given a graph or you can use your calculator and sketch your graph in your calculator. One thing to be aware of when you graph these things in your calculator is that a graph may be traced multiple times on a particular interval. So depending on the graph, it can be traced 2 or 3 or more times on the interval 0 to 2 pi. So you have to be aware of that when you're graphing these things. So if we're finding an arc length, for example, and our graph is traced twice on the interval from 0 to pi, we want to know that. So you need to be aware of that. So for example, if we were to graph r equals 2 cosine 3 theta, this is traced twice on the interval from 0 to 2 pi. So if we were given some kind of problem that involved r cosine 2 theta, and we were looking at the graph, we would need to be aware when we looked at the graph, or by plugging in some values and say, okay, our radius is 0 and theta is pi over 2. When is it 0 again? To get an idea of how often it is traced on that interval. So we have to be careful with that. In the book on page 718 talks about graphing this particular function by hand. We're not going to do much with graphing by hand other than to maybe figure out points of intersection or to figure out when our radius is 0, that kind of thing. So I'm not going to make you construct a graph of a polar equation by hand. Page 718 talks about doing that, talks about the process. This particular type of curve, r equals 2 cosine 3 theta, is called a rose curve. So r equals a cosine n pi, and r equals a sine n pi, or n theta, sorry, are rose curves. In your book on page 221, or 721, sorry, there is a chart with some common polar graphs. I want to do some demonstrations of graphs of different kinds of functions, just so we can see what they look like. But in your book, you can look at page 721, and they show some common polar graphs. And we'll look at those in a little bit. I have some demonstrations that graph some really cool polar functions. Yeah. All right, so the last thing I want to do is practice converting from a polar equation to a rectangular equation. So we're going to go the opposite direction that we did before. So we're going to do polar to the rectangular. Just to practice with this process. So the first one, r squared cosine theta sine theta equals 4. And we want to convert that to rectangular. So what can I do with this one? Yes, very nice. So I'm going to put an r with the sine and the cosine. So I'm going to say this is r cosine theta times r sine theta equals 4. And this tells me that xy equals 4. And that graph is what? What type of thing? Okay. Brady's doing this. So this is a hyperbola. So we would end up with something like this. That was a good visual.
Make Brady do it again.
Yep. All right. Second one. R equals 1 plus 2r cosine theta. What do we want to do with this one? This one's a nice one. Max says let's square both sides. Because if I square this side I get r squared. We know something nice for r squared. So I'm going to square both sides. R squared equals, and when I square this quantity, what do I get? 1 plus 4 r cosine theta plus 4r squared cosine squared theta. And then r squared is x squared plus y squared equals 1 plus 4r cosine theta is 4x, and 4r squared cosine squared theta 4x squared. And someone, was that you, Jacob? Jacob says let's write this as 2x squared. We could do that. That's fine. And I can rearrange this, and I get, if I rearrange everything, combine like terms, I get y squared minus 3 x squared minus 4x minus 1 equals 0. If we wanted to keep working with this to see what the graph of this thing would look like, what would we do? What's that? So one suggestion was let's have y on each side. We have a y squared and an x squared. Do you remember what we do with this? We could try to factor it. So what we want to do here is complete the square with x and y. So we would end up, so this gives us this is going to give us some conic section. It's going to give us some kind of conic section. So we would complete the square on x, complete the square on y, and then we would get a familiar looking function, some conic section. So when we get something like this, to get a more familiar equation, we want to complete the square. I'm not going to go through that now, but that's what we would do if we wanted to get a more familiar equation. That's our favorite thing from Algebra 2 and Pre-Calc, right? Completing the square.
No, probably integrals is my favorite thing.
But from Algebra 2 or Pre-Calc?
Yeah,
That's integrals from Algebra 2?
My favorite thing from algebra.
All right. Let's look at another one. All right, let's look at this one. R equals 4 cosine theta. What are we going to do with this one? Let's multiply by r. That's a good idea. r squared equals 4r cosine theta. So x squared plus y squared equals 4x. X squared minus 4x plus y squared equals 0. So let's go through the process here to figure out what this equation is. So I'm going to write this as x squared minus 4x plus 4 to complete the square, plus y squared, and I'm going to put a 4 on this side. So x minus 2 squared plus y squared equals 4. That wasn't too painful. So this equation is a circle with a center at 2, 0, radius 2. So this, if we were working with this in polar coordinates, this equation would definitely be easier to work with, I think, than this for a circle. One last one, and then we'll look at some graphs. R equals 4 over 2 cosine theta minus sine theta. What are we going to do here? Multiply. Let's clear that fraction. So I get r times 2 cosine theta minus sine theta equals 4. Distribute the r, so when I distribute the r, what do I get here? And then let's do the conversion as we distribute. So 2x minus y equals 4. So we get a line, 2x minus y equals 4. Now on this particular example, I would definitely rather work with something like this than something like this. This looks nicer to me than this. So sometimes polar coordinates are better, sometimes rectangular coordinates are better. So questions on our conversions. So tonight's homework is really just, it's all about conversions, converting coordinates and converting equations. And the questions on the quiz are just, I'm going to ask you to convert an equation from rectangular to polar and one from polar to rectangular. All right, are we ready to look at some graphs?
Yes.
Yes, I really like these graphs. You're not sure, right?
I don't know. Can I have a few minutes first?
You need to process a little bit?
Yeah, definitely.
Oh, look, they fixed my folders. I accidentally dropped one of my, or I dragged one of my folders into another folder on my network drive, and it won't allow me to drag it back out without administrative privileges. So I had the right to submit an IT ticket to get them to do that for me. No, they said, oh yeah, that happens all the time. Yeah, they were trying to make me. All right, let me see what I have here. The ones I found. All right, here's our first one. So our function is r equals 1 plus cosine 5 theta. So we're going to trace that out. So this line represents our radius. Can we see this? This is our radius, and the point is our point in polar coordinates.
Oh, the light.
Yeah, you want to turn the lights off? And there's our graph. So this is r equals 1 plus 4 cosine 5 theta. Isn't that a nice one? We get those petals inside the petals. Let's look at another one. Let's start with an easy one. Here's r equals cosine theta. We just talked about that one, right? R equals cosine theta. Come on. There's our circle. R equals sine 2 theta. And then we have a nice rose curve. Cosine 3 theta. Oops, it's already traced. So there's our trace. And see, this one gets traced twice. We talked about that one on the interval 0 to 2 pi. And we'll untrace it here. 1 minus sine theta. There's our cardioid. 1 plus 2 sine 4 theta. That one's nice. This is the one we first looked at. 1 plus. We looked at that one. That one's so nice with the petals inside the petals. Okay. Here's another one. Sine r equals sine of theta over 4. Look at that one. Sine theta over 4. That one's pretty crazy.
Can we make how to 3 shirts?
You can't.
Can we have that be like that?
Yes.
Harley, we can do
Yes.
This is like spirograph, right?
No. Alright, Seth's face faded with Seth's law and bold like over his face.
Oh boy. All right, so here we have, as we contemplate our shirts, sine theta plus sine cubed of 5 theta over 2. I'm not even sure what to expect here. Wow, that one's really cool. All right, I have more of these. Should we look at some more?
Yeah.
Okay.
These are height.
Let's see. Polar trace.
Turn up.
So this they say is flower-like polar plots. This might be, we might get. So this is r sine theta, and I'm not sure what it means by the numerator and denominator. This isn't the best demonstration. But we'll just pull the sliders and see what happens. Oh, there we go. So sine 2 theta, sine 3 theta, sine 4 theta. So these are all just different rose curves. 5 theta, 6, 7, 8. So imagine having to find the arc length of r equals sine 10 theta on the interval 0 to 2 pi. All right, and this changes the denominator on our fraction. There we go, sine theta over 2. Theta over 3. We looked at that one. That one's pretty cool. Whoa. Oh, we get the, so we're getting the. All right, so then we can also change the numerator for any of these. Oh, look at that. The numerator and denominator are the same.
Whoa! Yeah.
All right. I have one more of these. Let me find it. All right, so here's a very nice one. This is called the does it let us drag here? Well, this is kind of, I thought this would let us actually make the spiral, our logarithmic.
You can drag the k value.
Yeah, the k. Let's do the k. Because these are nice. Yeah, this one's not very good.
You can actually drag it.
Hit play.
It just changes the k value. It just changes the values. That one's not very good. All right.
That's not anything.
So let's. And I wanted to show you a couple of things that I couldn't find demonstrations for in. I have a couple in that I can do just manually in Geometer Sketchpad. So let me find that. There we go. So let's do the spiral first because the spiral is really cool. So we're going to graph function r equals f of theta, and I want so we're going to graph r equals e to the theta. That one's not very good. Let me go back. Let me change my values here. I'm going to try to get a nice. Oh, thank you. So now we're starting to get a spiral. Let me make this a little smaller, 0.001. There we go. Now we've gotten a spiral. So this is called so we get r equals e to the theta. This is a spiral. It's also called an equiangular spiral. Turns out that the tangent vector at any point makes a constant angle with the radius vector. So the spiral keeps spiraling around, and the tangent vector and the radius vector always make us an equal angle. So this is not a great, didn't do a great plot of the spiral. I was hoping it would look better. So let's look at one other set, one other type of equation. So we graphed r equals cosine, let's do cosine 3 theta. So we graphed that already. We get this rose curve. So let's think about what would happen. What would happen if I graphed the reciprocal of this? So here's our rows. I'm going to plot the new function. So I'm going to plot them together. So r theta. So I want to do 1 divided by cosine 3 theta. Okay. Yes. So we get everywhere that this one equals 0, we get an asymptote.
It's like a triple.
Like a triple hyperbola, yeah, it kind of is. And if we change our values, we could change this to a 4.
I knew the statement.
And then we'll change this one to a 4.
No, there'll be so many. So many.
So we get an asymptote everywhere that the denominator equals 0. So everywhere that equals 0, we get an asymptote. And we get this really cool graph. All right. Enough playing with graphs, I think. That was fun. I'm going to change that. I guess I can stop the video now.